after a certain amount of volume, then that will trigger the ventilator to allow for exhalation, which is the case in AC. Okay, so, all right. Let's go on here. SI and V, I'm just going to talk about it very briefly. It's a combo basically between AC and pressure support. Okay, meaning that you have a certain amount of mandatory breaths that the patient needs to get to set all those volumes are the same. Or all those breaths, I should say. All those breaths are the same. And then in between, you have independently generated pressure support breaths, which are just like your normal pressure support ventilation or spontaneous breaths. And then there's some breaths that are kind of a combo, where it's a mandatory breath, but then the patient's making an effort, so it's kind of a synchronized. That's where the synchronized comes in. So there are 3 different types of breaths. Now, the reason I don't want to spend a lot of time on it is because it was originally developed in the 80s to help with weaning, so that you could actually reduce the amount of mandatory breaths and increase the amount of spontaneous breaths and have the patient able to do more and get off the ventilator sooner. But actually, what happened was they found in studies that it's actually slowing people down. And the reason why it's slowing people down from removal of the ventilator. Why is that? Because the brain can't tell and the diaphragm can't tell which is a spontaneous breath and which is a mandatory breath. So it ends up actually delaying the whole weaning process. So as a rule of thumb, I actually never use SIV because I don't think it adds anything to other modes. It's certainly not better, and it may be worse. Okay? So rarely used. Okay, other modes, there are tons of other modes, which I'm not going to really discuss today. But just know that there are other things in process, and some of them may have advantages in certain subsets of patients. Okay, all right. I'm not going to talk about this. Okay, very briefly, sometimes we use this type of alternate mode called airway pressure release ventilation, in which, so usually you have a baseline, remember we have a baseline all the time, it's a peak. And when the breath is given by the ventilator, you have an increase in pressure because you're pushing the air into the patient at that point, up to a certain threshold, and then it will let the patient exhale, and that pressure is now diminished. So there's a PEEP, and then it goes up to a peak inspiratory pressure, and then it comes down to your PEEP. Okay, that's the cycle. Now, this type of mode is different. It's now saying that the PEEP, instead of very low, it's going to be actually very high. And instead of actually boosting pushing the air in to boost up the pressure, now we're starting at high, and we're just going to release the pressure, let the patient exhale, drop the pressure as the form of ventilation, okay? And the reason I bring this up into this is that there are a lot of ways to manipulate how the breaths are given. And this particular mode is now gaining a lot more favor in certain subsets of hypoxia and respiratory failure patients, like ARDS patients. The patients who do not respond well to the traditional AC lung protection, you may think of something like this. So just to keep in mind that there are different ways of giving the breath. Not just pushing in and taking it out, but dropping pressure and raising it back up. I know it may be a little confusing, but just so you're aware that sometimes you'll see that in the ICU. Okay, so respiratory system as a pump. So let's just back up. So remember we have the controller, we have the gas exchange, and we have the pump as all features of the respiratory system. If any one of these doesn't work, you have a problem with the entire mechanism of lung or respiratory system function. So starting with the controller, you need a brain to generate the impulse and have the nerves conduct that impulse to the mechanism, meaning the pump. In order for the pump to work, you need the chest wall, you need the muscles to all fire and contract, and all that to move so that the actual parenchyma of the lung can do the gas exchange part of the whole phenomenon. And any one of these things, if it's off, can lead to dysfunction. Now, when a patient is receiving support from a ventilator, you have to take into account what are the things that the ventilator is doing that are impacting that whole balance. And in terms of the pump function, you have to take into consideration what we call lung mechanics. Okay, so how is the pump functioning? There are two major things we look at in terms of how is the pump functioning. And we use that to adjust how the ventilator is now going to give the breath. Okay? So one of them is called the resistance of the airway, and the other one is the compliance of the respiratory system. And we calculate it in these ways, where we use certain parameters. I'm not going to get into a lot of detail about this, but to understand that there's a resistance that the ventilator has to overcome to get the breath into the alveolus to actually get the gas exchange going. And depending on what it is, you may have to think about certain ways to adjust the ventilator. The other thing is the compliance of the respiratory system. That means how is the pump how elastic is this pump actually being? So if you have, for example, a 400-pound person with a huge chest wall, you're probably going to have some issues with respiratory system compliance in a way that is different from someone who is very thin and has COPD, who has a very, very low compliance of the respiratory system. And for the obese patient, you have chest wall compliance that is a major problem. And in the COPD patient, you probably have more of a lung compliance problem, meaning a very low lung compliance. So we can use the ventilator to actually calculate these aspects of lung mechanics so that we can not only diagnose properly, but also provide the breaths properly. Okay? Oh gosh, this isn't for us either. Okay, so compliance. Not easy to measure. Okay, so just remember that the pump is basically it's a circuit that's arranged in series. You have the chest wall and you have the lung contributing to the respiratory system. That composes the respiratory system. Okay, the lung being the airway and the alveolar parenchyma, and then the chest wall is the pleura, the muscles of the intercostals, the diaphragm, the ribs, that sort of thing. Okay, so that is how you calculate it. So you have 1 over the compliance of the total system it's basically like a circuit in series. So chest wall compliance decreases. That means stiffness is present in the following scenarios. So a patient is obese, abdominal compartment syndrome. So remember, patients who are excessively resuscitated with fluids, for example, could be one potential cause for that. Any thoracic abnormalities, someone with kyphoscoliosis, for example, or some sort of trauma to the chest, flail chest, for example. Any other type of chest wall edema, just anasarca in general. All of these things can reduce the compliance of the chest wall. Okay, and that means that you're increasing the stiffness of the respiratory system by virtue of the chest wall only. Okay, which means that it'll impact how the breath is going to come in. It's probably going to have more trouble getting to a certain alveolar pressure. It'll affect the amount of work that the ventilator has to generate to get to the alveolar pressure that you desire. Okay, how do we minimize the contribution of the chest wall compliance? Well, you can sedate or paralyze patients, or you can imagine that if you do this, if the patient is working against or desynchronous with the ventilator and working after every breath or with every breath, that's going to be a problem. Okay, that's going to raise your chest wall compliance and potentially hurt your breath delivery. Okay, so sedate and potentially paralyze patients. Paralysis is rarely done. We should be rarely paralyzing patients, but sometimes we have to. Okay. Sometimes we can measure the pleural pressure with esophageal balloon, which we can't do here, so I'm actually not going to get into that, and that's actually kind of controversial anyway. Then the compliance of the lung itself alters depending on which phase of ventilation you're talking about. So inhalation and exhalation, there's a natural compliance of the lung which is different when you inhale and when you exhale. So that's also important to keep in mind. Okay. When we're on patients on a ventilator, we're limited, and we only can measure inspiratory mechanics. Okay. Although anyway, so all these have sort of assumptions and limitations, but they can be quite helpful. Okay. So peak inspiratory pressure is basically the pressure that's generated at the end of the inhalation phase of the breath. So like we talked about, most of the time we're going to be on AC mode. This is control. You have a baseline peak right? That's there all the time. And then when the breath is triggered, psh, the breath comes in, the pressure goes up. So the breath is being pushed in by the ventilator, right? That sends the pressure up, usually at a straight line, because we're getting in, depending on what the flow rate is, but assuming it's pretty steep. And then it gets to a certain point where either the breath is finished, or the maximum pressure, because you have the resistance of the airway as well as the alveolus, that leads to a maximum pressure. That pressure is called the PIP, okay, the peak inspiratory pressure. Okay? So that represents the pressure in the distended airway as well as the distended alveolus. So remember, you have if you're thinking about the lung as a one alveolar system, you have a tube, which is the airway, going to the alveolus at the end. Okay, so you have the resistance of both of these components adding to generation of this pressure. Okay, remember, pressure being flow times resistance. Okay, this is just the equation for that. So you can look at it as a function of the resistance of the airway plus the resistance that's provided by the compliance of the lung, which is generated by the alveolus. Okay, so this is how we use the lung mechanics into our conception of what is a PIP. The PIP is actually dependent on these lung mechanics. So if we can look at the PIP, we may have an idea of how the lung pump is working by thinking about the mechanic part of it. Okay. All right, plateau pressure. So this is one of the major things that helps us with compliance. Okay. Remember, the lung is elastic, and the plateau pressure is the pressure that's generated if there's once the breath is introduced and delivered in the inhalation phase, if there is a cessation of flow, that means if you stop, you basically have the patient has the tube, breath comes in, breath is terminated, but you close the valve, you don't let the patient exhale, and you wait for a steady state over 1 second. And you measure the pressure at that point. So now you're measuring the pressure in the alveolus at the end of the breath, inhalation phase. Okay? That's called the plateau pressure. And why is that important? Because it represents the mean pressure in all the alveoli of the lung. Again, we're assuming that all the alveoli are acting the same, which is not always the case. But if they are, that's our best surrogate. Okay? And that is the mean alveolar pressure is directly connected to the compliance of the lung. Okay, yeah. So depending on, if you think of the lung as a balloon, for example, you blow in the balloon to the maximum, and then you measure the pressure that the balloon is generating back at you. Okay, if you can measure it at the tip, that's your surrogate for how stiff is this balloon. Okay, if it's really wispy, this pressure will be low. If it's really stiff, the pressure will be high. That's going to tell you how compliant this balloon is, how compliant our lung is. Okay? You can't do it, you can't measure it when you're blowing it up or when you've let it go out, because then obviously the flow is going to affect the pressure. So you have to make it a steady state. Okay. So on the ventilator itself, you push this thing called the inspiratory pause. So once the breath comes in, there's a pause. You wait for a second, and you'll see the dip. There'll be a dip on the monitor. Okay, so you have the PEEP, breath comes in, you hit the inspiratory pause, there's a little dip, and then it's a plateau, meaning it's flat. That's why they call it plateau pressure. Then you let go of the inspiratory pause, and it drops back to your PEEP. Okay? So, so it includes the PEEP, remember. So we have to take that out when we're calculating the compliance. Because we're looking at really how does the pressure change on a volume pressure curve as you go from PEEP to plateau. Okay? If it's really stiff, then you're going to take it's going to take a lot of pressure to get to that volume. If it's very non-compliant, if it's very compliant, then it's going to take only just a little bit of pressure to get to a certain volume. Does that make sense? It's just a classic volume pressure curve. All right? So here you have it. The compliance is basically volume over pressure. So for a certain amount of volume, depending on what the pressure is to generate it, like if you have a very stiff balloon, it's going to take a lot of pressure to get that same amount of volume into the balloon, right? Whereas if it's really wispy and really moth-eaten, whatever, then it's going to take just a little bit of pressure. Okay? Yes?